Good morning, everyone, or good afternoon, depending on where you are. I guess these days you don't quite know where folks are. So I'm going to start off by just kicking us off and giving a quick overview of EPIC processors and how we're structured and how security fits into the processors, and then Andy will go into some pretty cool detail on the implementation and the product in Google Cloud. So I just want to start off by saying EPIC processors are just a great general purpose processor. We have 170 world records. We have a lot of solution briefs on our website. If you guys want to go if folks want to go take a look at a whole bunch of different applications, almost all general purpose code runs well on the EPIC processors, especially with our second generation, where the performance is increased, and then we'll talk a little bit about that. So we're very focused on providing solutions for the cloud, and that really means providing the density, providing the capabilities that the cloud needs. And now more and more, we're really pushing the envelope on advanced security features. AMD has a long history of innovating in the server. We were back in 2006 or a little before then, we invented 64-bit for the x86 instruction set. And so we're really with the SEV and this security technology, going back to our roots and innovating and pushing that forward. One really cool thing this is off of Google's GCP website is our partnership with Google has been very deep, and we go back many years back to the Opteron days. And this is a picture from 2008, where we're showing on the left here. This was the millionth server that Google actually built that was based on AMD. Fundamentally, our two companies are so aligned. We have a common mindset of both openness and innovation, and that this approach really manifests itself in our security capabilities and and what we're talking to you about today. So go to the next slide. So what is fundamental to the performance and the capabilities is this Zen 2 core. And this of course, is available on our laptops and desktops, but most importantly, in our servers for targeting cloud. And it utilizes the 7-nanometer technology. It's actually the world's first 7-nanometer product, and it's for x86, and it really drives a tremendous amount of performance and density. Really, two different compute density. We're two important things in the cloud, and in particular for cloud service providers. We see the core itself is extremely powerful. We've seen a significant uplift over our Zen 1 core, and then also this core is just extremely competitive against a lot of other other processors that are available in the market, and we've been able to show some extremely good results on it. And then we have this very innovative interconnect technology, which I'll talk to you in the next slide. But basically, we structured the device in terms of chiplets with a main IO die chiplet that has the memory interfaces, that has the PCIe connectivity, and then these little 7-nanometer core chiplets that have the L3 plus a complex of up to 8 CPU cores. This distributed architecture allows us to scale extremely efficiently and to be able to get to some of the densities that are needed for our key cloud applications. This has been a key differentiator and a huge part of our success is being able to roll out and drive this capability. It also allows us to leverage the latest process node technology that's available, like 7-nanometer. So in there, key feature is this AMD secure processor that's shown here, and that's one of the key parts of our value proposition here is that we have security in hardware, and that allows us to, offer security solutions that are much more close to the metal, and will and provide an overall secure solution So we have built-in root of trust, the dedicated hardware subsystem, and additional ISET to support instruction set extensions to support these transitions. All right, so next slide. So there's a little bit of detail on the hardware memory encryption. We started this a while back. We started off with what we called AMD Secure Memory Encryption. What this did is it secured the entire memory region with a single key. And then we evolved this to the Secure Encrypted Virtualization, SEV. So now the first iteration of this was really focused on encryption of the entire memory. What we've done with SEV is been able to extend the encryption using a virtual key for each of the virtual machines. Architecturally, as I showed you in the previous slide, you have the chiplets that have the x86 CPU, and then you have that main I/O die that actually contains the secure complex. So they're completely separate, and that's very important. It means that there is a fundamental separation between the CPUs that run the hypervisors, the guest OS, and the secure processor, which maintains the keys that are used with the memory controller. And so what we've done is we've created this pretty cool architecture where the secure processor is able to understand and map keys into map the keys for the memory controller to for each of the virtual machines that are running in the memory. All right, and so it's altogether this provides us with a pretty robust security system for each of the virtual machines. All right, so with that, I'm going to take it over and give you guys a quick poll question.
Awesome. Thank you, Kumaran. So, yeah. All right, guys, if you can answer this. Are you currently running workloads in the cloud with a service provider offering cloud instances powered by AMD EPYC processors? Yes, no, or I am unsure. We're going to give you guys a couple seconds to answer that question. You can let us know. Okay, let's check out these results. Looks like most of our audience isn't. All right, well, I will turn it over to you, Andy.
All right, well, so first of all, I want to talk a little bit about, what Kumaran said. I think, we agree. We've seen these performance improvements as well. We have our AMD server, our offering is our N2D instances on Google Compute Engine. So that's with these processors. These have higher memory bandwidth. They've got higher core counts, more memory, and we're seeing cost per compute savings up to 13% based on certain workloads. And those are generally available in Google Compute Engine. But I'm mostly here to talk about security and confidential VMs, which is a feature that I'm personally really excited about, which is currently in beta. Before I get into that, I want to talk about cloud security in general and overall, because I think people think about the cloud and they think about security a lot, and they often are concerned about security when moving to cloud. And I want to come back because I'm a firm believer that in the fullness of time, the cloud will be the safest place for anyone to store their data. And I think that's sort of governed by the economics. Because if you look at the move to cloud, it's about economics and scale. When you come to a cloud provider, cloud providers can achieve savings from scale. And when you think about that, you usually think about the meat and potatoes of data center, like the machines and the racks and the power and the space and cooling. And that's why it's cheaper to move to the cloud. And that's true, but the most important thing to make your system secure is security expertise. And if you're not in the Fortune 50, let's say, or some of the largest companies in the world, you just can't afford and aren't going to spend the resources on security that the hyperscale cloud providers can provide. And the more that you cede control and the more you use the features and enlighten the cloud provider to be able to do things for you, the more security gets taken off your plate and gets done by people that are probably spending a lot more time and resources than you. So now I'm going to talk about how can confidential computing help you. So it's a new layer of defense with AMD SEV. Encryption of data at rest, encryption and data at transit. These have been things that have been talked about for a long time. This is introducing something new, which is essentially encryption of data in use. So even while it's in the RAM of the machine. some great use cases. There's multi-party computation. You can actually share data with another party without actually exposing that data. Let's say you want to compute something that you need both data for without actually sharing the data with each other. This enables that. It allows you to protect your sensitive data and code, or both. Help mitigate your data protection compliance risks, which we all have compliance things. Confidential computing can help with that. There's some reporting. So, there's a lot of confidential computing solutions out there. Why are we big advocates of confidential VMs with AMD SEV? The biggest one is usability, ease of use. So on what we've implemented on Google Compute Engine is you can actually create a new VM, and if you pick a supported operating system, it's really just a checkbox to make it to be a confidential VM. So you don't need to change your application. All of the changes that need to be made are done in the OS level. So they're managed by either Google, if it's a Google OS, or the operating system vendor, and in the cloud provider level. So there's no need to rewrite or redesign or rethink your applications. We're a huge fan of usable security. I think usable security that gives you a fair amount of security is always going to be better than very, very hard to use security, which gives you a ton of security, because with very, very hard to use security, nobody uses it, or nobody uses it right, and it's too complicated. The other thing that's really nice about confidential VMs with AMD SEV is the performance is great. Like, there isn't really much of a performance change. We have some details there if you want to read the details, but confidential VM doesn't impose a very large security benefit. And when you think about something like encrypting in use, there are a lot of solutions that are performance prohibitive. So I'll go a little bit about how it works. So from Google Compute Engine's point of view, yeah.
Cool. I'm just going to ask, what type of customers do you see wanting to adopt confidential compute before you go into the details?
Yeah, sure. I mean, I think there's different categories of customers. I think, at our recent Next on Air event where we sort of announced this, JP Morgan was a guest speaker, as they've been an early adopter and early interested customer. And I would say, broadly speaking, financial institutions are one of the biggest customers, just because they generally are very tech savvy. They're aware of technology clearer than most people. It's still a very new technology. And they're usually sort of very up on the new trends, and they're very security sensitive. So, I think the nice thing about confidential VMs is that because it's so easy to use, it kind of appeals to anyone who's security sensitive and is willing to put a little more resources into security. And so another big one is governments. Government agencies and entities, sort of worldwide, are interested in using this as a protection mechanism. So those are probably the two biggest. But again, I think we see interest across all sectors. I think Google Cloud is very big into retail, so we see a lot of retail interest. But I suspect that's because that's a huge an area for Google. So kind of across the board, but focused most on security conscious customers.
Oh, that's great.
So, thanks. So how it works from a confidential point of view, from a GCE point of view, it looks just like a regular VM. So anything you could run on a VM is going to run on a confidential VM. The way it actually works, so the memory is encrypted in the RAM. So, Kumaran talked a little about this, but that it needs to be decrypted for the CPU to run on it, obviously. So it gets decrypted by the memory controller when it gets pulled into the cache. So what that means is it's only decrypted when it's inside the CPU package, right? Because the cache is inside the CPU. Now, the platform security processor is what manages and generates keys for this. So when you launch a new VM, it generates a random ephemeral key. You can't get it out of the platform security processor. There's no instructions to get it out. There's no API to get it out. It's meant to be the hypervisor cannot read that. So the hypervisor can't get it out. So it keeps this memory encrypted. Now, there's one question I always get, which is, well, that doesn't make any sense. Like, there's got to be some way that the hypervisor needs to communicate with the guest operating system, because there are things like devices, there are things like interrupts, there are things that require a communication channel between those two. So, and of course, it supports that. So what happens is that the guest can select pages to share with the hypervisor. So the guest operating systems, and Google did a lot of work here to select which pages are going to be shared with the hypervisor. So the guest is in complete control of that. and then the hypervisor reads those pages. If the hypervisor tries to read a page that the guest did not share, it's just going to read encrypted junk, and it's obviously not going to know what to do with that. So, and then the other thing is, we're huge fans of the scale of these processors. You can have huge VMs, and I know a lot of security solutions impose limitations to scaling, and confidential VMs with AMD SCV doesn't do that in any way, which is sort of a great win from our point of view.
Hey, Andy, what kind of guest OSs are currently supported on the confidential compute? Yeah.
So one of the things that I sort of hinted at and glossed over is that your guest OS has to support it. So because it's a new technology and it really changes the underlying way that the operating system and the hypervisor communicate, there needs to be operating system support. So there is support in upstream Linux. It's making its way into the distributions. Right now on Google Compute Engine, again, I said we're still in beta. So right now we support 2 operating systems. One of them is Ubuntu. I believe it's the latest version, 16 or 18. And then the other one is what we call the Container Optimized OS, which is a Google-specific Linux distribution for containers. So if you use Google Container Engine, it's the OS that's used there, so that's already supported. Or if you run your own containers and you want to run Kubernetes on Google, the Google Container Optimized OS is what we recommend, and that one supports SCV as well. We're hoping to have Red Hat Enterprise Linux soon, and then sort of build on the other distros from there. But it is in upstream, so one of the nice things is everything is being done upstream. It takes some time to get integrated and supported by the operating systems, as well as some time for Google to test it and make sure it works and all those other things.
Oh, great.
Okay. So moving on. So, some just like, so what kind of threats are we protecting against? I think it's worth, being sort of explicit about what threats. And I think, one of them is accidental data leakage. By having data encrypted, there's always, ways in which it could leak that this would really mitigate, which is more or less how encryption is used in most places. Protects against malicious administrators. It protects against, I call them curious neighbors, so neighbors that have found certain classes of bugs that leak information. I won't get into specific. I don't want to get super in the weeds of like which bugs are mitigated versus not mitigated, but many of them, things that very rare to begin with, but can prevent those. It's sort of another layer of protection, and then it protects you from cloud infrastructure bugs. I mean, we try to avoid these, and we don't have very few of them, but it's sort of another layer of protection to make sure that those are mitigated. And then I'll kick it back to the Q&A, I believe, or to Tiona.
Awesome. Thank you so much, Andy and Kumaran. That was a great presentation, and it was so great to learn about the benefits and features of the Google and AMD EPYC partnership. All right, y'all. So we have some time for questions, we have some questions in here that I would love to get to. Just a reminder to make sure to open up your Q&A widget at the bottom of your screen and submit your question now. Alrighty, so let me see. The first question I'll get to here is for you, Andy. Can I upgrade from a regular N2D VM to a confidential VM, or do you need to start from scratch?
You need to create a new VM. So one of the things that I talked about is that the OS has to support it. So you have to pick a supported operating system, and you can't take an existing there'd be kernel changes that sort of that's an unsupported workflow, I guess is what I'm trying to say. And I think technologically it'd be hard to support, so I don't know that we're going to try to enable that soon.
Okay, awesome. Thank you. All right, Kumaran, I'll direct this question to you, and I think Andy too can answer. Can you compare and contrast the security offerings from the competitors to our current products, specifically SCV versus TME-MK TME?
Okay, so I'll start off by talking about our solution. So what we have really in the EPYC-based processors is very hardware-centric security. So it's really close to the metal, we don't depend on. We try to minimize the number of changes that are needed in the software layer, and we as Andy has just very articulately talked about, it's really the changes are at the hypervisor and more specifically the guest in the virtual machine, the guest OS that needs to change. We don't actually do any changes. No changes are needed at the application level. So we don't use the secure enclave type of concept that actually has to make you change your application code. We're really this is implemented at the guest operating system level, and that's reflective of the fact that we have the controls in hardware, and so we're talking directly to the memory controller, which actually has that embedded encryption decryption block per virtual machine. So we can support I think altogether 509 different keys and decryption. So up to like 509 virtual machines, for example, can be supported within one EPYC processor. I don't know, Andy, if you have any other comments or thoughts and observations.
Yeah. I mean, I can give you sort of our point of view, because I think Tiana asked about NKTME, and I think your answer was a little bit closer to the SGX, which is a different technology. And I think there's SGX, which has that enclave, which is sort of the enclave model, which, the reason why we prefer SEV over there is, again, just ease of use. I think if you take a technology that requires you to rebuild your application, you'll probably get some extra security benefit because you've refactored your application in such a way to with security as the first thing you have in mind. And putting something in a small enclave does make it very small, which is good for security. But at the same time, if you do that, if you put that much work in, there's probably lots of security you can get. On the other hand, with SEV, you're able to get a good amount of security with very little effort. So as I said earlier, like, usable security beats hard to use security every time. I'm a firm believer in that. Now there's another solution, NKTME, which I think is a little bit less, has some security, is less secure than SEV. It doesn't have the attestation piece. It doesn't have as much guest control, sort of in terms of controlling the pages. So that's kind of why we like SEV over NKTME. So it's kind of like there were two questions to compare it to, but so we chose one mostly because it's easy to use and has good security properties and hits kind of right in the middle.
Awesome.
Or we're just the right trade-offs of easy to use and good security properties. And also, we overall, the EPYC processor this generation has just had great performance. So it's always good to put something on that where the base performance level is good, and you're going to get support from the non-security people who are going to want to use this processor.
Wonderful. Thank you both, Andy and Kumaran. All right, so we have another question in for you, Andy. Is Google also supporting other architectures like ARM or on confidential computing?
So our I'm not going to talk about sort of the future because I don't have a crystal ball. But I can say that from right now in Google Compute Engine, we support x86 only. Might the future be different? It might be, but it sort of depends on where the demand is, depends on where the technology is, depends on what the total cost of ownership comes out to be. So that's where we're at. But we are paying attention to it. But we certainly don't. I'm not going to announce plans to support or launch anything.
Okay, awesome. Thank you. Kumaran, I'll direct this to you. What is the performance hit, if any, when memory encryption is enabled?
That's a great question. So I guess in tests with real workloads, we've seen 10% or less. And actually, I'd like to get Andy's feel for what they've seen within the Google Cloud environment. If you do go to our website, we do have performance briefs, in particular that talk to the confidential compute benchmarks that we've run on the Google N2D on the AMD website. So I encourage you guys to go check that out, because I think there's some really valuable data across different workloads. But I'd like to see what Andy's perspective is from a GCP point of view, user point of view.
Yeah, I mean, from what we run in our tests, we have a variety of performance tests that we run for basically every time we launch anything new, because we want to make sure we didn't accidentally, make performance bad. So we've seen somewhere between 2 and 5%, so pretty small numbers. I think, it's highly dependent on workload. Things that are latency sensitive, like TCP/RR or message passing workloads, tend to be close to that 5. And then there's some compute heavy workloads, like I don't think we have a Bitcoin mining benchmark, but things that are essentially compute heavy, or gzip or kernel, things like that are on the lower end of that. It's closer to 2%.
Yeah, that makes sense, right? So the more memory intensive, the higher the performance, but yeah, still the performance is still with very, very well bounded.
Yeah, the performance hit comes at memory page or cache miss time, right? So if you're having a lot of cache hits, it's much lower. And then there is a memory cost, but it's so small it's almost not worth mentioning. I don't know what it is.
Wonderful. And everyone, those performance benchmarks that Kumaran mentioned earlier are featured in our resource center, so feel free to check those out there. And we'll get to one more question for today, and I'll direct this to you, Kumaran. How are the keys managed, and is there an option to use an external key manager?
So the keys are managed on chip, and that's part of the hardware security regime, right? So that AMD secure processor that we showed in that first few slides, so that's separate from it's physically separate from the compute dies. It's integrated into that I/O die portion near the memory controller, and it itself is a complete secure embedded controller that runs independently. And I'd like to, and Andy, I don't know if you have any more comments on how Google manages it, but it's designed so that neither AMD nor Google would see these keys, and they're secure and inaccessible from a user perspective.
Yeah, I'll weigh in a little bit. Yeah. So everything you said is true. So you can't control the key. Part of the security benefit is that the key is in this PSP that you can't get out. Now, what we're building internally, and what I think is going to eventually be how this works with external key managers, is there's an attestation piece to this, to attest to a remote authority that it is the correct state, and then you could release a key based on that state and use that key. So the SEV key itself is always going to be in the PSP, but then you can come up and make sure you're in a clear state and release a different key that you protect all of your data with. Right now in the beta, that's managed through the TPM, which you'll have on your VM. So there are use cases where a TPM will make an attestation from the VM, asserting that it did come up with SEV turned on and in a good state, and then a external key manager can release a key to that. We don't have tooling to make that easy, but it is on a roadmap.
Awesome. Thank you both, Andy and Kumaran. All right, everyone, we are just out of time for Q&A today, so if we didn't get a chance to answer your question during the webinar, feel free to email us using the Contact Us widget at the bottom of your screen. I just want to highlight a few things before we bring the session to a close. Please visit the AMD Partner Hub for tools and resources you need to sell and market AMD products. We also have AMD Arena, our new incentivized training program where you, our partners, are rewarded